Cogeneration simply means we're producing two different forms of energy or more than one useful form of energy. So normally when we talk about a Rankine power cycle, we're talking about the electric work output. But here, since it's cogeneration, in addition to the power output, we're also providing certain heat input. Okay, or certain we are heating up some other working fluid. So the outputs from the cycle that we're talking about are two: electric power or electricity plus heat, and it's certainly coming from the same energy source. Now, why do we care about that? Let's have a look. If you consider a lot of industries that are around us, right? So a lot of them, they require energy in the form of heat as well, in addition to, of course, electricity requirements. And this is, I mean, this is called basically process heat, simply because it's needed for certain chemical processes, right? Certain food processes as well. So when you talk about the conditions of the process heat that's used in these industries, it's typically in the range of 150 to 200 degrees Celsius and between 5 to 7 atmospheric pressure. So sort of medium temperatures, slight medium to low to medium temperatures, like not very high temperatures. Now, the way the heat is produced in all these industries is actually by burning fuel. Okay, so you're burning fuel, and all you're doing is just producing steam at rather low temperature and using it. And this is this is what's done, but it's again a not very let's say smart way of using your fuel, right? Because the fuel can burn at 1500 K or even higher, and all you're doing is to heat up water to about 473 K and use it for heating purposes, not anything else. So it's not a very efficient way of making use of the resource, nor is the temperature between the source and the application well matched. So there could be better options, but yes, a lot of industries still do this because, well, it's a cheaper option. Why not? So now the question is, how can we make this entire thing a little bit more better from exergy point of view and also from the economics point of view? So it turns out that a lot of industries that require huge amounts of process heat, they also require large amounts of electric power. Okay, so it makes sense to actually make use of the hot water that you have at the end of the hot water that you have from the boiler. Once you burn some sort of a fuel, and to use that to actually produce some work output, and then use it to produce heat, right? So I mean, instead of just heating it directly to 200 degrees Celsius, you could heat it to maybe 400 degrees Celsius, and then use extract some amount of work, and then use the rest for providing the heat input. Okay, so why waste it? The other way to look at it would be, well, you have a electricity, you have a power plant operating already. How about using some part of the steam and providing the process heat and uh, reducing the amount of heat rejected to the environment, right? The simple idea is, well, we want to produce power and heat, or we want to give electricity output as well as some meet the heating requirements. Now, when you do both of them, the plant that you have is what's called as the cogeneration plant. Okay, and we'll have a look at schematic in a bit. Now, when we talk about the industries that fit into this definition of requiring a lot of process heat as well as consuming large amount of electric power, well, the industries that come to mind are a lot. I mean, refineries for one are one such industry where they're using lots of process heat and they're using lots of electric power. It's for this reason that a lot of Aramco refineries have their own power plant, right? They don't take power from Saudi Electric Company. They have their own power plant because the power plant is needed for running the refinery itself, right? And it makes a lot of sense there. And refineries also need a lot of process heat. They need a lot of steam at these temperatures, 150 to 200 degrees Celsius, for performing a lot of chemical reactions that are needed to improve the fuel or to transform the fuel into the chemicals that are needed, right? When you guys, I mean, some of you will surely end up in Aramco for your co-op or your summer project, and when you go there, you'll be seeing how they make use of process steam or this process heat in a lot of different chemical processes, right? Apart from refineries, food processing plants, such as the ones that Almarai has or any other company has, these make use of the process heat. So They don't have their own power plant, but they can have smaller power plants that can provide heat as well. The other option would be district heating, but essentially the point is any place you need hot water plus electricity, this sort of application makes sense. Now, to give you more specific examples closer to home, Aramco has more than 3 cogeneration plants within the eastern province. So these are the locations: Ras Tanura, Joema, and Osmania and Shidgam. And these power plants are actually producing 1 gigawatt power plus 2 million kilogram per hour of steam, right? Pretty huge quantity of steam. And I mean, they're using all of this for their chemical reactions, right? We're producing millions of million barrels of oil, so certainly you need an equivalent amount of water for producing the stuff. So yes, this is not something that we are just talking about in theory. It's something that's actually there, and it makes a lot of sense when you look at the energy utilization point of view. Now that we have talked about a lot about what is there, how it works, and so on, let's look at its schematic and understand what's exactly happening. So this is the schematic for a cogeneration plant. It's very similar to what we have seen for a feed water heater, okay, specifically the closed feed water heater, in the sense that we allow some part of the steam to expand within the turbine, and then we extract some part here, say of certain fraction, 15% or whatever, and send it through this heat exchanger where it transfers heat to the process fluid. Okay, either you use it directly or you heat up some chemical directly, or you transfer it to another fluid that goes on and heats provides the heat input. It's your choice, but this is the typical stuff used. Now, as expected, this is at this heat exchanger operates at a pressure which is higher than condenser pressure, lower than the boiler pressure, and so when we want to send it back to the condenser, we have to reduce its pressure, and we do that using a trap, which is simply an isenthalpic expansion device, right? So it comes down from the heat exchanger pressure of 0.1 megapascal to, which is about 1 bar, to the condenser pressure of 0.1 bar. Okay, so this is a very flexible operation, right? Depending on what you need, you can play around with the flow rates that you send. So let's say you have certain times when you need a lot of process heat. So instead of sending anything to the second stage, we send everything to the heat exchanger for providing the process heat. That is, we can make y is equal to 1. Okay. Now this is one way of doing it. This is one of the common ways in which you're doing it, but you can also have a valve here straight away to send it directly to the heat exchanger without sending through the turbine, right? Although not commonly used, because it always makes sense to extract some amount of power within the turbine, but you could do that if you want it, right? If the heat input, if the process heat requirement is very high. Okay, so when you do that, when you don't send anything through the second stage turbine and send everything through this process heater and let it expand, so you're not rejecting any heat in the condenser because you're sort of bypassing the condenser, right? And it's a very efficient way of using the exergy available. There is other option in which sometimes where we may not be requiring a lot of process heat, right? It happens from time to time in a given day where your process is done and you don't need process heat for a certain period of time. So there, instead of just sending it through this heat exchanger and wasting the energy, you could just make y is equal to 0 and send everything to the second stage turbine and expand it, just like you do in a typical power plant. Okay, so multiple options, multiple ways in which you can do it, but essentially it's a very simple concept here. All right. So let's quickly go over the energy balance for this, and then I'll take questions. So when we talk about the energy balance, it's going to be very similar to what we have done before. The only thing that we need to be careful here is the fact that the mass flow rate is going to be different through different components. Okay. So you have mass flow rate m.1, let's say, entering the turbine, but when you talk about what's going through the heat exchanger, it's y times m.1. All right, and what goes through the second stage turbine and back to the condenser is 1 minus y times m.1. All right, so you got to be careful about what flow rate you're talking about. Otherwise, it's pretty straightforward. So let's look at the different flow rate, the different energy balances. Now, in terms of the heat input, it's simply m dot 1 times h1 minus h5, right? So this is all what we have. Heat output, well, when it's happening within the condenser, we need to be careful about the mass flow rate because it's different. It depends on y. Y could be 0 as well, but depends on y. Okay, so it's m dot 1 times 1 minus y times h3 minus h4. Okay, so difference in enthalpy across the inlet and exit of the condenser, and the mass flow rate associated with it. Now, the process heat, right? The process heat is simply m dot the mass flow rate associated with it, which is y times m dot 1 times h2 minus h6. Okay, and the work done for the turbine would simply be broken down into two: m dot 1 for the first stage and m dot 1 times 1 minus y for the second stage. Okay, so as long as you're careful about this, it's a pretty straightforward thing, right? There's no problem here. All right, questions. This thing is there in your homework as well, so you might as well ask questions if something is not clear because you have to use this. Okay, no questions. All right, then let's move forward.
Doctor, if it's not,
Yes.
if it's an ideal, we don't use 1 minus y.
You mean if it's a non-ideal, or then
If
what
it's
do you?
ideal,
You mean what? The expansion within the turbine?
the whole process.
Mm-hmm. No. Whether it's ideal or non-ideal, it does not really matter. We will keep using y and 1 minus y. If it's non-ideal, the only thing that will change is the enthalpies at the exit of the turbine, right? So if you look at this, so let's say, I mean, this is the, let me just write it properly. So this is state 1, the entrance to the turbine, and you have another pressure here, okay? And normally, if you have an, say, ideal process, there'll be an isentropic expansion. So state 2 would be somewhere here. But in an actual case, there will be some entropy involved. So this isentropic case, let me call it 2s. What you actually get at the exit will not be 2s, but actually 2, right? So the enthalpy at the exit of the turbine at each stage of the turbine would be different, but y simply refers to the fraction that you're sending. Okay, so the uh, the the fraction y would remain the same, and these energy balances are again the same, will remain the same whether it's ideal or non-ideal. The values for these enthalpies would be different, right? So H3 would be different because H3 would be something that you need to calculate from the definition of isentropic efficiency for the turbine. Okay, it's not the H3S that we get by simply assuming constant entropy. So that will be the change that we have. Does that answer your
Okay, thank
question?
you.
Okay.
Yes.
All right, so then let's move forward and solve an example on exergetic efficiency and cogeneration. But before that, a quick review of exergy because we're going to make use of it again. So this is the exergy balance for a closed system, and this is the formula for specific flow exergy. The reason I'm showing it here is because we're going to solve a problem based on that. And when you do the problem by yourself, you can have you can refer to the slide and have a look on how to make use of that. Okay, so just to remind you, when we are looking for exergetic efficiency calculation for any given component or for the entire system, we make use of the exergy balance equation, right? And this is the exergy balance equation that we have here. There are some really good examples in your textbook, example 8.7 and 8.8, where the exergy or the exergetic efficiency is calculated for specific components, right? Like a heat exchanger or turbine and pump. These are sort of similar to what we did in chapter 7, so please make sure to go through them. In this class, I want to talk about the calculating the exergetic efficiency for the entire system, right? We already covered the individual components in chapter 7. So the other thing I want to talk about now is to remind you about the exergetic efficiency formula when you have a heat engine, right? So exergetic efficiency, as I said before, is also called the second law efficiency. And when we're dealing with the heat engine, you can calculate exergetic efficiency simply as the ratio of energy-based efficiency divided by the Carnot efficiency. Okay, the Carnot efficiency would simply be a function of the temperatures TH and TL. All right, so this is again something that we discussed before. Just wanted to remind you again. And so just wanted to tell you that exergetic efficiency is something that you can get either from exergy balance, or for heat engines, you can get it from this formula. Okay, and why do we care about exergetic efficiency? Well, the simple reason is because we would want to identify how much where the irreversibilities are and how much exergy is being destroyed, so that we can figure out ways to minimize the exergy destruction wherever it makes economic sense. Okay, so now let's go ahead and look at this question. So here we are dealing with a cogeneration system. Okay, the Rankine cycle operates with the steam which is entering the turbine at state 1 of these conditions, 55 bar and 370 degrees Celsius. So that's state 1. The condenser pressure, right? This is the condenser here. The condenser pressure is 12.4 bar. The isentropic efficiency of the turbine is given. Okay, the energy which is rejected by the condensing steam is actually transferred to a separate process stream of water, which is entering at 1 megapascal and 120 degrees Celsius. So this water is entering as compressed liquid, and it exits as saturated vapor at, of course, the same pressure. So we are not rejecting the heat to the environment. We are rejecting the heat in a heat exchanger to another process stream of water. Okay, that enters at, that is operating at a different pressure. So this is certainly a non-contact type of heat exchanger, right? We are having two streams at two different pressures, and it comes in at lower temperature and exits as a saturated vapor at a slightly higher temperature, the Tsat. Okay. Now, for this specific problem, we need to do a couple of things. We need to first determine the mass flow rate for the working fluid. The working fluid is the water here, but here we're talking about the working fluid within the cycle, right? And if the mass flow rate of the process stream, which again is water, but it's the process stream, right? It's the thing that's going in here, is 22,700. So this mass flow rate is given, m dot p is given. We need to calculate mass flow rate of the cycle. Okay, this is the first thing. The second thing that we need to do is we need to devise and evaluate the exergetic efficiency for this overall system. Okay, the overall cogeneration system where you're providing work output plus some heat output. Okay, so this is what we want to do. Now, before we go ahead and solve for mass flow rates or anything, or even the exergetic efficiency, in all these sort of problems, we need to sort of define the states and get the values of enthalpy and entropy. Okay, and that's what we will do first. So this is how the TS diagram looks like. And here we are having 2s and 2 simply because the exergetic, the isentropic efficiency is mentioned. Okay, so the process, the expansion within the turbine is not isentropic, although the compression within the pump is isentropic, right? Because there's nothing mentioned about the isentropic efficiency of the pump. Okay, so now let's very quickly look at how we get the enthalpies and entropies at all the different states. We have done this before, so I'm going to go rather quickly. Any questions? Feel free to stop me. So state 1 is easy. We have the pressures and temperatures, get it from the superheated vapor table. For state 2, we got to make use of the isentropic efficiency. Okay, so first of all, what you do for state 2 is you determine the enthalpy at state 2s. And the way to determine enthalpy at state 2s is pretty straightforward. You have the pressure, and we have the entropy as well. S2s is equal to S1, right? That's what happens in an isentropic process. Now, using this value of S2s, you determine the quality of the mixture S2s. And using that, you determine the enthalpy H2s. Okay, now this is what you have. This is what we have done before as well. Now you have S2s, you have H1, and you have the isentropic efficiency given, right? And again, to remind you, the isentropic efficiency for a turbine is simply the actual work output divided by the ideal work output, okay, or the isentropic work output. So we have everything known here. The only thing that's unknown is S2. So you plug in the numbers, and S2 comes out to be 2,838. And if you recall, we mentioned that the enthalpy that comes out here, S2, is always greater than S2s, right? So that's what you see is the case here as well. And I mean, it makes so it's a quick sanity check to ensure that you're doing the correct calculation and you're putting the things in the right order. OK, so why does S2 have to be greater? Well, the work output is smaller, right? The actual work output is smaller. Sorry. So OK, we have state 1, state 2, and state 3 is very straightforward. State 3 is simply saturated liquid. Nothing is mentioned, but you know, it's you can assume the exit of the condenser would be saturated liquid. So you don't have to bother anything. You already have the condenser pressures. So you get what's needed. State 4, well, to determine the enthalpy, again, we got to make use of the pressure difference between state 4 and state 3, and also the specific volume at state 3, right? So it's an incompressible liquid. We've already discussed how to do this. We make use of this reversible work input formula. Now we need to go to state 5 and state 6, right? We have determined the 4 states for the working fluid. Now for this other process stream, it comes in at a pressure of 10 bar at a temperature of 120 degrees Celsius. Now from the table, we know that this is compressed liquid phase. And for compressed liquid phase, well, we discussed that it does not, the properties such as enthalpy, they don't depend on the pressure so much. They depend on the temperature. All right. So all you need to do is get the value of HF at this value at T5 of 120, and you get the enthalpy at that. We also would want to do the same thing for the entropy. We're going to make use of the entropy here. OK. State 6 is again straightforward. You know the pressure, you know the quality. OK, the quality is given as saturated vapor. Pick up the numbers. Straightforward. So this is how you build the table. Now the real work starts after you have built the table, right? In the exam, when this, or even in the classes, if I give you this sort of a question, I'm not going to ask you to determine all the properties in the table. I may give something easy, maybe to determine enthalpy for state 1. Then I may give something like maybe to determine enthalpy at state 2 and maybe state 4, right? Just to make sure that you understand how to do the stuff. But you'll be spending a majority of the time in also looking at how to make use of it. OK, so the first thing is we need to determine the mass flow rate of the working fluid within the cycle. OK, so any ideas? How do we determine that mass flow rate? We have the mass flow rate of the process stream. We are having heat exchange from this, the heat loss during the process 2 to 3 is the heat gained during the process 5 to 6. OK, that's all what we are having within the heat exchanger. So how do we get the mass flow rate of this working cycle, or the mass flow rate that's going here from 2 to 3?
Energy balance or mass balance?
Yep. Energy balance. We don't do mass balance here because you know, the mass is remaining same in both of the cycles, but excellent. The answer to this question most of the times is energy balance, right? And when the masses are changing, you take mass balance as well. Thank you, Abdul Malik. So you just have to put energy balance here, right? So whatever, so you can put the energy balance in either way. You can just write it as the energy lost by the hot fluid is equal to the energy gained by the cold fluid, or you could also write it as, you know, summation of MIHI is equal to summation of MEHE, meaning the mass flow rate and the enthalpy coming in has to be equal to the mass flow rate and the enthalpy going out. There are two inlets at state 2 with the mass flow rate of m dot cycle, and state 5 with the mass flow rate of the process stream, which is given, right? Either way, you end up with the same equation, same energy balance equation. And here we have the values for all these enthalpies, H2 to H6, right? We also have the mass flow rate of the process stream, m dot p. The only thing we don't have is the mass flow rate of the cycle. Once you plug in the numbers, this is what you get. OK, so 2.5 to 10 power 4 kilogram per hour. It's a reasonably high mass flow rate, but sort of smaller than the flow rate that we were looking at in previous examples. So this is as simple as that, right? It's a very simple problem testing your concept of applying the energy balance. And this is, again, as I mentioned before, these are the sort of questions that you can expect, right? I mean, questions which test one concept at a time. All right. This is done. So now let's look at the second part, which is to evaluate the exergetic efficiency for this overall system. Okay, so till now we have been looking at the exergetic efficiency for the compressor, for a pump, for a turbine, and so on. We have not looked at the exergetic efficiency for the entire system. Okay, so so the way we solve it is pretty similar, as we'll find out in the next few minutes. So you just have to basically remember the exergetic efficiency formula, right? I mean, the exergetic efficiency is simply desired output by required input. And here you got to be careful in figuring out what is the output, what is the input, and everything needs to be written in terms of exergy changes, right? And you get the exergy changes from simply the exergy balance equation that you have. All right, so here we're not looking for each component, we're looking for the entire cycle. Okay, so when you look at the entire cogeneration system, the desired output that you're getting here is the network output that we obtain from the turbine, plus the exergy transfer that's happening to the process stream, right, which is happening here in this heat exchanger or in the condenser. Now, for this desired output, which consists of two different things, work plus heat transfer, we need to provide some input, and the input is simply the exergy increase within the boiler, right? We need to heat up the fluid. So that's the simple exergy input that we are providing. All right, sorry. So coming back to this, I mean, we certainly expect there to be some difference between the exergy input and the overall exergy output, simply because there will be some irreversibilities. Okay, and that is what is the exergy destruction. So the question is, what is the exergetic efficiency here for this case, right? How high is it? So here we just need to write the net rate of exergy output, which we said is coming from the network output of the cycle, plus the exergy increase of the cold fluid. Okay, so we got to be careful to make use of the exergy for the process stream and not use the sorry, the exergy decrease of the hot stream, because those two values could be different. Okay, energy balance and energy works out, but the exergy is not balanced. So you got to be careful about when you're using this. Same way, we just have to write in terms of the input is just the exergy input to the cycle, right? Exergy input that's happening within the boiler between stage 1 to 4. Now, the work input, the net work output of the cycle, it's simply turbine work minus pump work, and it's something that you can easily determine, right? We have all the 4 enthalpies, we have the mass flow rate of the cycle, so it comes out to be pretty easily in this manner. Okay. Now, the other thing that we need is the change in exergies. Now, the change in exergies are also easy to determine once you have the enthalpies and the entropies. All right, and we picked up these entropies directly from the table. So we have the enthalpies and entropies for all the 4 states, just a matter of plugging in the numbers in this formula, and you get the exergy changes for both the process stream here and for the working fluid here. Okay, so once you plug in the numbers, you got to be careful to make use the correct mass flow rates. Okay, this is the mass flow rate of the process stream. This is the mass flow rate of the working fluid. Okay, once you make use of this of the correct mass flow rates, correct changes in exergy, the exergetic efficiency comes out to be 92% almost, right? It's pretty high, and it's simply very high because we're making use of it of the almost all the exergy available, right? There is some amount of exergy destruction, but I mean, from an energy balance point of view, the energy efficiency would be even higher than this. Okay, so yep, that's about it. If you have any questions, you can stay back and ask me. Otherwise, that's the end of the class. See you guys on Sunday, inshallah.